In section 5, we already introduced and discussed parametric differentiation. Now that we've defined what a second order derivative is, it's probably time to have a look at second order parametric differentiation. And this you can find in your lecture notes in section 6.5. If you remember what we've covered in section 5, you will remember that we can calculate dy dx for a function that's defined in terms of a parameter, for example t, as essentially calculating dy dt and then dividing by dx dt. If we want to calculate the second order derivative, you might be tempted to think that it would be just the ratio of the second order derivatives, but that is not the case. It means that if you want to calculate dy dx, this is not the same as just calculating the second order derivatives. You cannot do this. This is not correct. And we will see a general expression that you could use if you want to obtain the second order derivative of a parametric function. But as we'll see, as long as you can do parametric differentiation and you obtain the first one, you can always differentiate it again, which is exactly what we're going to do following the lecture notes in section 6.5. Let's follow the lecture notes, section 6.5, and try to second order differentiate the following parametric function. Based on what we've seen in part 5, section 5, it is relatively straightforward to obtain the first derivative. What we need to calculate on one hand is dx dt. In this case, this is simply 1 minus sine of t, and the other ingredient is dy dt, which in this case is cos of t. Parametric differentiation tells us that we can obtain dy dx by the ratio of dy dt and dx dt. So this means this derivative is cos t over 1 minus sine t. Obtaining the second order derivative means we need to differentiate this again, so why not just try it? If we want to obtain the second order derivative, why not just apply the operator d dx, which means applying it on this side as well. Let's try to write that therefore the second order derivative of y in respect to x is all about differentiating cos t over 1 minus sine t. This is where your knowledge of chain rule and very soon quotient rule really come into play and really help you. Now, in this way, we need to use a chain rule, and essentially we can write that this is the same as d dt of the expression we have, that's cos of t over 1 minus sine of t times dt dx. And again, thinking in terms of Leibniz notation, we would see that we could cut the dt's, get the dx back, and we get it back. Getting to the stage, what we need to use is the quotient rule. We have the quotient of essentially a function that's cos t, one which is 1 minus sine t, and then we're multiplying by dt dx. And remember that these are my small t's, these are not f's. If we do that, quotient rule tells us that we get the denominator, that's 1 minus sine t, times the derivative of the numerator, that's minus sine t, and then minus the derivative of the denominator, that will be minus cos of t times cos of t. And we're dividing everything by the denominator squared. And we're still multiplying by dt dx. What we can now do is use the inversion rule, which we also talked about and introduced in section 5. And the inversion rule, in getting rid of this, tells us that dt dx can be obtained essentially by getting 1 over dx dt. And we've already calculated what dx dt was. It was 1 minus sine t, which means this is 1 over 1 minus sine t. And therefore it means we can sub this back in here to write essentially minus sine t. Then we're multiplying minus sine t by minus sine t, that's plus sine t squared. And then we have plus cos square of t. And we're dividing by 1 minus sine t squared times 1 minus sine t. And therefore we end up with 1 minus sine t raised by a power of 3. One of the final things we can do is to recognize that this is actually 1. And therefore, with a little bit of good old physics 101 magic, we've cleared the board just enough to write that the second order derivative at squared I over dx squared, this is the notation we're using, is given as 1 over 1 minus sine t squared, and it is squared because the 1 minus sine t cancelled one of the exponents and we dropped it to 2, with this being our final answer. In general though, we can write down an expression for second order parametric differentiation in case you want to do it in one go, but it is quite useful to just focus on first of all doing first order parametric differentiation, then using chain rule and quotient rule and doing simple re-expressions, for example remembering the inverse rule and then being able to get the final answer without having to memorize this formula. But in case you want to, you can memorize it and just use it. So let's have a look at the formula. This is how it looks like. And this is how you would obtain second order parametric differentiation essentially in one go. And it means you need to calculate the terms you will already require for the first parametric differentiation, that's the dx dt, dy dt. You then need to multiply them by the second order derivatives, essentially dy dt, dx dt, and then you divide by dx dt to the power of 3. In the previous example, one of these terms was the same as the dx dt, and therefore we were able to cancel out, but this is not always the case. The important message though is that you don't need to memorize this formula. You can if you want to, but you can always get there by using the simpler differentiation rules. Another topic we need to cover in section 6 is second order implicit differentiation.